Okay, so section 11.2, all about combinations. So we're going to look at what is the difference between a permutation and a combination, the number of ways of selecting elements instead of arranging them, and problem solving with the NCR notation. So permutation, that's what we did in 11.1. This is an arrangement of objects where order is important. This is the big key. Let's star this. It's so important. That's what a permutation is. Order is important. So for example, if I had 3 letters, remember we did that example where we had A, B, and C, and we saw that there were 6 unique arrangements or permutations of those letters. Those are all the different arrangements because every one of them is different because order is important. So permutations are, in the 11.1 section, we did numbers, words, codes, passwords, lineups, any kind of an arrangement with an assignable role, task, or position. Now let's compare that to a combination. A combination is an arrangement where order is not important. So this is the big difference here. So if I was talking about those 3 letters A, B, C, there's just one combination because it doesn't matter which order that I select the objects as long as they are selected. So in a combination, A, B, C would be the exact same thing as A, C, B. So you know when you go to your locker and you have a combination lock because you enter in a combination, now that we know the definition, we should actually really call it a permutation lock because the order is important. Because if your combination was 924 and you went in and entered in 429, it would not work. So when you think of combinations lock, think permutations because order does in fact matter. Combinations are kind of like fruit salad. If you have fruit salad, the order of the fruit in the salad doesn't really matter. Like if you look at that bowl of salad, you could say it's a strawberry, raspberry, banana, blueberry salad, or you could also say it was a banana, blueberry, raspberry, strawberry salad. It doesn't matter the order. So this distinction is really important. So I want to do a question here where we're going to look at just classifying something as either a permutation or a combination. For every single one, I want us to ask the question, is order important? If the answer is yes, it's a permutation. If the answer is no, it's a combination. Okay, so here's context A. Entering in a 4-digit password. Is the order important? Well, yes, the order is important because if you don't enter in the correct order of the numbers, you're not going to gain access. So context A is 1, a permutation. Context B, choosing 5 people for a committee in which 1 person is the president, 2 people are vice president, and 2 people are secretaries. Is order important? Well, the answer to this is yes, because there are assignable roles, tasks, and position. President is different than vice president is different than secretary. There is an order to these people. So permutation it is. So context B is 1 for permutation. C, selecting 3 paintings to be hung on a gallery wall and then arranging them side by side. So we have 2 things going on here. We have the selection process. That selection process, that's a combination. So the selection process, I'll put it up there as a combination. But then we're arranging them side by side on the wall, and that's a permutation. So altogether in this question, we have both permutations and combinations. So context C, we'll classify that with a number 3 to show it is both. Context D, reaching into a bag of 10 marbles and picking out 2 marbles. Is order important? Well, the answer to that is no. It doesn't matter what my first marble is, what my second marble is, because I'm selecting 2 marbles. It doesn't matter the order in which I do that. So that is a combination, making context D number 2 for combination. Okay, let's try another one. Okay, 2 examples here. Mateo wants to take 3 dogs with him on his morning walk. If Mateo owns 8 dogs, now Mateo is my son and I could totally see him owning 8 dogs because he loves dogs. How many different groups of dogs can he choose for his walk? So does order matter? I'm selecting 3 dogs to go on the walk. Does it matter if I select this one first, that one second, or that one third? Maybe to the dogs it might matter because they think they're not going on the walk, but really it doesn't matter. It's a combination. We're just selecting the dogs. Doesn't matter the order. Now let's compare that to example number 2. There are 8 dogs in the cutest dog ever competition. How many ways can first place, second place, and third place be awarded? Does order matter? Well, you can hear first place, second place, third place. So there's an arrangement in order of the dogs. So this one here would in fact be a permutation. And just as an aside, my dog Hershey would take first place. Just saying. Okay, let's calculate each one of these. So 8 dogs in the cutest dog ever competition. How many ways can first place, second place, and third place be awarded? We already established that this is a permutation. Let's calculate how many ways. So there are 8 dogs. So there are 8 choices for first place, although really it should be Hershey, so just one. For second place, 8 dogs in total, but we already gave away first place. So 7 choices for second place. Third place, 8 dogs. We've already given away first and second place, so really only 6 choices for third place. Okay, multiply those together and you get 336 different ways you can award first, second, and third place. Okay, now let's compare that to the taking dogs for a walk. Okay, so taking dogs for his morning walk, he owns 8 dogs. How many different groups of dogs can he choose for his walk? Does the order I choose the dogs to go on the walk matter? We already said the answer is no. Well, let's look at how many ways I can arrange the dogs. Okay, so this is the number of ways that I can arrange 3 dogs when order matters. So this is an arrangement, we'll say, with order being important. Now, since we said order doesn't matter, so since order doesn't matter, we should divide by the ways of arranging the dogs. Since it doesn't matter if I pick this one first, second, or third, well, let's look at those 3 dogs. There are 3 times 2 times 1 ways of arranging them, which is 6 ways. So 336 ways of selecting the 3 dogs. Since order doesn't matter, which one I choose first, second, and third, we divide by 6. So there are 56 ways of selecting 3 dogs out of 8 to go on the morning walk. So that is the difference between a permutation and a combination. So notice this question here for a combination. We took all of the permutations, which is the arrangements, and we divided by the ways of arranging the 3 dogs. So this is the permutation of the 8 dogs, and this is the ways of selecting the 3 dogs. Okay, that's why it's a lower number. Let's look at a shortcut to figuring out combinations. So if I wanted to know, for example, the combination of 9 objects taken 2 at a time, I first look at the permutations, the ways of selecting 2 objects. So 9 choices for the first one, 2 choices for the second. But since it doesn't matter the order that I choose the objects, I look at the ways of arranging the ones on the bottom, 2 times 1. So 9C2, let's expand that. So 9C2, you take your number 9 and you expand it 2 times. Why 2? Because there's a 2 there. 9 times 8, that's the permutations on top. Then I take the 2 and I expand that 2 times 1. So looking at this, I can see a nice way to simplify it because 8 divided by 2 is 4. So this is really the same as 9 times 4, which is 36. Let's try that again. So if I have 8C3, so what I'm going to do is I'm going to take 8 and I'm going to expand it. Whoops, there we go. I'm going to expand it 3 times. 3 times. So 1, 2, 3. And then I take my 3 and I expand that 3, 2, 1. Okay, so looking at that, I've got 3 times 2 is 6 on the bottom with a 6 on the top. So it just simplifies to be 8 times 7, which is 56. So that's a nice little shortcut way of expanding these and simplifying them without actually using my calculator. Okay, let's look at a question. How many ways can 6 players be chosen from a team of 15 athletes if Amber must be included as one of the players? Okay, so if I'm looking at this, Amber must be one of the players. So let's just take Amber out of the picture entirely. So I don't have 15 athletes, I have 14. Amber has to be on there. So I'm not really selecting 6 players, I am selecting 5. So what I'm really looking at is I am looking at the combination of 14 athletes taken 5 at a time. So let's use that shortcut that we did before. We're going to take 14 and we are going to expand it 5 times. 1, 2, 3, 4, 5. And then we take the 5 on the bottom and we just expand that as well. 5, 4, 3, 2, and 1. And then we just look for some common factors to simplify. So I see that 4 times 3 is 12, so 12 divided by 12 is 1. And I see, 5 times 2 is 10. 10 divided by 10 is also 1. So I'm really just left with 14 times 13 times 11. Okay, so I can just put that one into my calculator, and I see that there are 2,002 ways of doing that. Okay, so now that you've had a little bit of a taste of a combination, you don't have to do it by hand for every question. Let's look at how you could do it. So permutations were fundamental counting principle factorials, or NPR notation, because order matters. But combinations, the order doesn't matter. So we take the permutations and we divide it by the ways of arranging the objects. So the number of combinations, NCR, can be given by the following formulas. Okay, so here's the formula that I was just talking about right here. It is permutations divided by ways of arranging the objects. And if you look at it, here is your formula for permutations right there. That's the formula that we did. That's the NPR formula. And we're just dividing it by the extra R factorial. So this formula is on your formula sheet. Now this right here, I'm just going to highlight it for you, is a notation. So we don't use the rounded bracket notation very often. This is on your formula sheet, but we need to be familiar with that. So I could use NCR, or I could use this notation with rounded brackets, NR. They mean the same thing. So just be able to recognize that as a notation. Now, just like we had a permutation button on our calculator, we also have a combination button on our calculator. So that's math probability over to number 3 for combinations. So let's look at that. For the combinations, I'll just show you again where that is, and I'll show you if you have a CE calculator where that will be. Okay, so we were doing permutations last time, so here's where my combination is. Math, go over to probability, and then you can see it is option number 3, so math probability 3. If you have a CE calculator, you can go alpha window, and then you can see that combination is option number 8, so alpha window 8. So those are the ways that you access it on your calculator. Okay, let's try some examples. So I know that these questions are in the combination section of your notes, but every question, let's just ask ourselves, does order matter to determine if it's truly a combination? Because on a test or the diploma, they'll be all mixed together. They're not going to be in sections. Okay, so for this one, employees use their cooking skills in a chili cook-off. Employees were required to select a specified number of items from the following list. So we have list A, which looks like your meats, list B looks like your tomatoes, list C is your vegetables, list D is your beans, and list E is your spices. Now, does it matter the order in which I select those? Like for list 3, I have to select 3. Does it matter whether I select the onions first, second, or third, or as long as they're selected? So the answer to that is order does not matter. So if I want to know how many different chili recipes are possible, I have to select from each of the lists. We've already established it's a combination, so let's go ahead and do that question. So let's start with list A. So list A, I have to just select 1. So there are 2 meats and I need to select 1. So I look at 2C1. List B, I also select 1. This time there are 3 choices and I select 1 of them. List 3, there are 4 different vegetables there and I need to select 3 of them. Order doesn't matter again, so it's a combination. List D, I have 3 different types of beans and I need 2. And then list E, I have 4 different spices and I need 2 of them. That didn't show up very well. Let's do that again. 4C2 for list 2. So all I have to do is put that into my calculator and multiply together, and I get 432 different chili recipes. Okay, let's try another one. If there are 10 points on the circumference, that means the outside of a circle, how many triangles can be formed using these 3 you're using these 10 points. So if you think about making a triangle, let's grab a triangle here. Okay, to draw a triangle using those points, I need 1, 2, 3 points. So I need any 3 points on there. So does it matter if, let's say I chose these guys here, does it matter if I connect the dots this way, if I go 9 to 6 to 3 to 9? Is that a different triangle than going maybe 9 to 3 to 6 to 9? It doesn't matter, okay? So this is a combination. The order the points are connected does not matter. So there is in fact a combination question. There are 10 points on the circle and I want to select 3 of them. So I just look at 10C3 on my calculator, 120 ways of doing this. Okay, after a business meeting, there were 120 handshakes. If every person at the meeting shakes hands with everyone else, how many people were at the meeting? Okay, to do a handshake, I need 2 people. So I need 2 people for 1 handshake. Does it matter whether person 1 shakes person 2's hand or person 2 shakes person's 1 hand? Does it matter the order in which they shake hands? In fact, it doesn't. You just need 2 people to shake a hand, so this is a combination question. So we don't know how many people are at the meeting, but we know that we need 2 to do a handshake, and there were 120 handshakes that occurred. Okay, so we're going to solve NC2 equals 120. So I have your combination formula there. Let's go ahead and simplify it. So using our formula, it's n factorial over n minus 2 factorial equals 120. Okay, first thing I noticed down here, 2 factorial, that's just a number. 2 times 1 equals 2. So to get rid of that, I'm going to multiply 2 by this side of the equation. And to be fair, this side of the equation, just to get rid of that. Let's just deal with that first off. So I'm going to have n factorial over n minus 2 factorial equals to 240. So hopefully this looks familiar. We did a whole bunch of questions like this in 11.1. So to simplify things with the factorial, we are going to expand the bigger, which is the n factorial. So start with n and then go 1 less, go 1 less, and I'm going to stop right now because I have a matching factorial. Okay, so now that I have a match, that cancels, and I'm left with n times n minus 1 equals 240. Or applying the distributive property, n squared minus n. Because it is a quadratic, I will set it equal to 0 by subtracting 240 from both sides, and then I will factor. Okay, now that I've factored, I just set each factor equal to 0. And then I look at my answer. So how many people were at the meeting? Were there 16 people at the meeting, or were there negative 15 people at the meeting? Well, hopefully you recognize you can't have a negative number of people, so this is an extraneous root, meaning it's a solution to the quadratic, but not to the actual question. So that tells me there are 16 people at the meeting. Now, of course, I can check this on the calculator, and I'll show you that like this. So I was trying to solve NC2 equals to 120. So first of all, I can go straight into the table because it is a number of people. I know it would be a whole number. So I went in the table and I scrolled down until I looked and found 120, which was the number of handshakes. And I saw that there were 16 people at the meeting. So I know I did that correctly. Now, when we do combination questions, a lot of the times card questions come up. Now, if you're using a card question on a diploma, all the information you need to know about cards will be given to you in the question. So don't worry about that if you're not someone that's really familiar with cards. I just want to give you a quick little run through in terms of cards. There are 52 cards in a deck. Half of the cards are black, half of the cards are red. So 52 divided by 2 gives me 26 cards that are black. 52 divided by 2 gives me 26 cards that are red. Now that breaks down even further. Of the 26 cards that are black, 26 divided by 2 equals 13. There are 13 spades and there are 13 clubs. Of the 26 cards that are red, 26 divided by 2 is 13. There are 13 diamonds and 13 hearts. So you can see that each suit, there are 4 of them, hearts, diamonds, spades, and clubs, has 13 cards in them. Okay, in addition to that, there are 12 cards that are considered face cards, face because they actually have a face, and those are jacks, queens, and kings. So this diagram is in your notes, and you guys can refer to it as often as you need to for the questions. But on the diploma, they'll give you everything you need to know in the question. So let's try a question. How many 5-card hands contain at least 3 red cards? Now, first of all, are card questions combinations? So if you think about it, if you have 5 cards, if you've ever played cards before, the first thing I do is I resort my hand based on the game I'm playing. So it doesn't matter the order in which I have my cards in my hand. So it is a combination, because having, for example, an ace, 2, 3, 4, 5 is the same hand as having an ace, 5, 4, 2, 3. Those are the same thing. So card questions are in fact combination questions. Now, as soon as you hear that you have a 5-card hand, my tip to you is to always make sure you have 5 cards. So we're asking for at least 3 red cards. And hopefully you remember that at least is a minimum. And minimum means I have cases. So out of the 5 cards, if I have 3 red cards, I could have 3 that are red, I could have 4 that are red, or I could have all 5 that are red. Okay, so let's look at all our cases like this. So my tip, making sure you have 5 red cards. If you have 3 cards that are red, you have 2 cards that are black, because 3 and 2 have to add up to 5. If you have 4 red cards, you must have 1 black card that goes with it, because 4 and 1 is 5. If you have 5 red cards, you know you have no black cards, because 5 and 0 is 5. So always make sure they add up to 5. So let's look at our red cards first. We're going to look at having 3 red cards. So 26 red cards in the deck, and I want 3. 26 red cards in the deck, and I want 4. 26 red cards in the deck, and I want 5. Now let's look at my black cards. 26 black cards, I want 2. 26 black cards, I want 1. 26 black cards, I don't want any. Okay, so I can put all of that into my calculator, quite a bit to enter, and I get that there are 1,299,480 5-card hands having at least 3 red cards. Now, that's a lot to enter into your calculator. So I have a little bit of a tip, because notice these are all 26, okay? They're like 26C3, 26C2, C4, C1, C5, C0. So instead of entering in those all at a time, so instead of entering in 26C1, 0, 1, 2, 3, 4, and 5 individually, there's a little trick that you can do in your calculator. Okay, let me just show you that. I have it in your notes, but let me just show you what that looks like. Okay, so what I'm going to enter in is 26. That's your number, and then we're going to go in and get our combination. So math over to probability, down to combination, or my CEs, you're going to go alpha window to get into your combination. And I want 26C0, 1, 2, 3, 4, and 5. So what I'm going to do is I'm going to access these squiggly brackets, which are right above your rounded brackets. These brackets here just denote set. So I'm looking at 26C, and I'm looking at the set of 0, 1, 2, 3, 4, 5. Of course, close your bracket. And so what the calculator is going to give you is it's going to give you the set of 26C0, 26C1, 26C2, 26C3, 26C4, 26C5. But the keystrokes, much easier. And you press enter, and there you go. So the first one is 26C0, 26C1, 26C2, C3, C4, and C5. Once you have those numbers, I have to use my arrow to get over to see all the digits there. I think that's much easier than doing them all one at a time. Okay, so those are all of the steps there. Okay, let's look at some common, oops, this should say common combinations. Let's just change that. These are common combinations, similar to when we did permutations. Okay, so NC0, there is equal to 1. So see 5C0 equals 1. There's always one way of selecting 0 items from n items. NC1 equals to n. So for example, 5C1 equals 5. So there are n ways of selecting one item from n items. And NCR is the same as NCN minus R. So what I mean by that, here's an example. It's easier to see it with numbers. 5C2 is 10 and 5C3 is also 10. The reason is because 5 is made up of 2 and 3. So if you look at that, 2 plus 3 equals 5. That's why they're the same thing. Selecting 2 objects is the same as not selecting 3 objects, or vice versa. So that's kind of a little shortcut that you can look for. Let's actually use that. Okay, so we know that NCR is equal to NCN minus R. So we're going to use that to find the value of X. So 43C19 is the same as 43C what? Let's use our formula here. Okay, so I have 43C19 is the same as 43CN minus R. 43 minus 19. So that means that 43C19 is the same as 43C24. So the value of X is 24. And again, this works because 19 plus 24 equals 43. So having 43 objects and taking them 19 at a time is the same as having 43 objects and not picking 24 of them. Okay, let's look at another one. Remember that weird notation for combinations that I told you to look out for? So this is 7C2 equals 7C5. So this is just a notation for combination, which just means this. So I want to show that these are the same. So let's use our formula. 7C2 is 7 factorial over 7 minus 2 factorial, 2 factorial. That would be the same as 7C5, 7 factorial over 7 minus 5 factorial, that's the permutation, and then divide by the ways of arranging the objects since order doesn't matter. So tidying this up, I have 7 factorial over 7 take away 2 is 5 factorial equals to 7 factorial over 7 take away 5 is 2 factorial, 5 factorial. So hopefully you guys can see those are the same, but let me just highlight it for you. I have a 7 factorial on top, and then I'm dividing by a 5 factorial multiplied by a 2 factorial. Since the order that you multiply numbers doesn't matter, you can see that these are exactly the same. So we've shown that they're the same. Okay, let's try simplifying an expression. So I want to simplify NC5 over N minus 1C3. So this is going to be a big fraction because this in the numerator is a fraction and this in the denominator is also a fraction. So we're going to have a fraction over a fraction. So in this question here, my tip is to write it as a division instead so that you don't have a fraction over a fraction. Okay, so NC5, that is, let's try that again. So NC5 right here is n factorial over n minus 5 factorial, 5 factorial. And that will be equal to n minus 1C3. So that's going to be n minus 1 factorial. Oh, this is divided, not equal to, sorry. This is divided by, there we go. N minus 1 factorial over n minus 1 minus 3 factorial, 3 factorial. So that looks much easier to work with. Okay, so I have n factorial over n minus 5 factorial times, now 5 factorial is just a number, 5, 4, 3, 2, 1, which is 120. Okay, so I'm going to keep my first fraction the same, change division to multiplication, and flip my second fraction. So this denominator becomes the numerator. So n minus 1 minus 3 is n minus 4 factorial, And then 3 factorial, 3, 2, 1 is 6 all over n minus 1 factorial. Okay, so we are going to simplify this together. So since I'm multiplying, I am going to group it as one big fraction, or I can simplify each one separately. So really, there's two different ways that you can do it. So let's just simplify each one individually. Remember I said when you're simplifying factorials, you expand the bigger one. So n factorial is the bigger one. Over here, you expand the bigger one, which in this case here is in the denominator. And then I'll write it as one big fraction. So I'm going to expand the n. So n, 1 less, 1 less, 1 less, 1 less, and 1 less. And then I can stop because I have a match in my denominator. Okay, and then I'm going to multiply that by, in this one here, I'm going to expand the denominator. So n minus 1, 1 less, 1 less, and 1 less. I can stop because I have a match. N minus 4 factorial times by 6. Okay, so for here I have my n minus 5 factorial and n minus 5 factorial cancel. Here I have n minus 4 and n minus 4. So I can group this as one big fraction. Let me just do that. So 6 in the front times n, n minus 1, n minus 2, n minus 3, n minus 4, all over 120 in the front, and then n minus 1, n minus 2, and n minus 3. Grouping it as one big fraction, you can see there's more I can simplify. So all together, oh, I can simplify my numbers as well. 6 and 120 have a common factor of 6. So I'll divide that, and I end up with 20 on the bottom. So all together, I have n minus 4 on top, all over 20. So that is the way I think most students would do it. But I want to go back here and show you what I see as a more efficient way of doing it. So I'm just going to copy this over to a new page and just show you what I mean. Okay, so if I go back here, after I've expanded it and canceled my factorials, notice I grouped it as one big fraction as I can with multiplication, and then I simplified to my final answer. So I want to go over here and just show you a different way of looking at it. So because multiplication of two fractions you can combine as one just by multiplying the numerators and multiplying the denominators, I just want to show you an alternate way of looking at this question. It's not better than the other way, it's just different. So I just want to give you another way that you could look at this, just combining it as one big thing. So the reason I want to point this out is because as I was doing the question, I noticed that a couple of the factorials were closer than the other one. So instead of doing n factorial and n minus 5 factorial, I'm going to look at n factorial and n minus 1 factorial because those are much closer together. And then I'm going to look at n minus 4 factorial and n minus 5 factorial just to simplify them. So let's see if we get the same answer. So looking at my blue, n factorial and n minus 1 factorial. This one is the bigger one, so I'm going to expand that one. Now looking at the yellow, n minus 4 and n minus 5, this one is the bigger one, so I'm going to expand this one. And let's just see what we get. So n factorial, I do 1 less. Oh, and then I can stop because it already matches. So it already matches my n minus 1 factorial on the bottom. Now let's look at my yellow. I'm going to expand n minus 4. So n minus 4, and then 1 less. Oh, and look, I can stop because that matches my n minus 5 factorial there. And so then I still have my 6 and my 120. So in doing it this way, I think it looks a little simpler. N minus 1 factorial, n minus 1 factorial, minus 5, and minus 5. So all together I would be left with n times n minus 4. And now I can just look at my numbers, 6 and 120. So again, we said it was a common factor of 6, and I would be left with 20 on the bottom. I think that looks a little simpler, but either way is fine. You can see you do end up with the same answer. And I would actually check the answer to this just to make sure I'm correct. So if you look at the original question, I would do the original question in Y1, and I would do my answer in Y2 just to see if I get the match. So original question in Y1, answer in Y2, and you can see the check always happening in the table. They are equal for all permissible values, so I know I did that question correctly. Definitely worth it. Okay, so to summarize, permutations are arrangements where the order is important. So we're looking at things like numbers, passwords, assignable jobs, roles, or tasks. Combinations, the order is not important. So I'm just selecting objects. I'm looking at committees with no roles, assignable jobs, tasks, or positions. Card questions. And again, combinations are the number of permutations divided by the ways of arranging the objects, since the order does not matter. So if you look at this, I like this little rage cartoon here. So I read it as 7 factorial over 4 factorial, 3 factorial. How other people read it, angry voice because it's an exclamation, 7, 4, 3,